All right, let's start. Welcome back. So last time, well, just before we start where we are in the class, we are in good shape to finish chapter 5 soon. I would be surprised by Thursday, but who knows, maybe. And then after chapter 5, that's finished for homework number 2. And I think so. I'm not too sure. Maybe there's, I'll have to check. But for the midterm, for sure, it's finished after chapter 5. So then, because that's more than enough. So it's everything that has to do with sets, with yeah, linear systems, with matrix algebra, and all these things. Yeah, so I'm going to post the second homework. Yeah, probably Thursday, Friday, if I'm really late, Saturday, but hopefully not. And you should have a few moments to do it, 2 weeks or 3 weeks, something like this. I'll check. That first time it was 3 weeks, right? So yeah. Yeah, and then that's good enough practice for the midterm. Then the midterm is coming back from the break, which is beginning of March. Then, yeah. So it's quite late, but it's to give you enough time to prepare and study everything. And then the last part of the class is all about derivatives and a bit optimization, a bit about Taylor expansion. Yeah, it's a fun part. This year, I feel that the last part of the class was less well received than this part. So I'll try to make it not too difficult. Okay, so today we continue on our journey towards finding out whether systems have solutions. So it's so last time I didn't really introduce all that many new concepts. I barely tried to make a link between the old vector thing and linear independence of vectors and algebra and linear independence of algebra itself and the determinant. And what we have learned is that zero determinant means that the system has no solution or no unique solution, and that the vectors making either the rows or the column of the matrix are themselves linearly dependent within each other. And now this, I'm sure it's going to be more of a liking for people who just want to learn how to do stuff. So today we just learn to do stuff, okay? So it might look complicated, but yeah, so bearing with me, it's very useful. So first concept is Laplace expansion. So this is a way to compute the determinants. So let me just write out how you do it in a very high level way, but nobody learns this way. It's just to state out how you do it. And then I'm just going to show you by example, and everything's going to be clear. So, and if you think it's complicated, then sorry, that's how math works. So I didn't choose. So for a matrix, so let's have an n by n. Yeah, and sometimes I've been lazy and not adding parentheses, but yes, in the book they have parentheses. And we're going to have that n is greater than 1, because you cannot really have a whole big expansion with a single term in it. So here's how we're going to compute the determinant. So it is going to be, so you might remember from last class how we did things. Well, it's the same thing. It's just I'm rewriting it in a formal way. So it's the sum I 1 to n of -1 to the I plus j I aij times the cofactor of aij. That's how I write it. And so this is if I go from row 1 to row n, but I could do also the column, do it column wise, and it's the same thing. So here, all I would have to do is to just change the G. So I can use the columns or the rows. And now, if you think that this doesn't make any sense, I agree with you. It's complicated. So, but everything's going to make sense when you start doing it. So I and J are between between 1 and 2. So we say that this thing over here, AIJ, is called the minor of A. Yeah, M it is. The determinant of A without the row I and column J. And minus 1 I plus J. Times AIJ. I definitely have some bullet points there. Is called, so this is just to know what we're talking about, a cofactor. I'm not very big fan of learning all these terms. Sometimes I forget them. So the important thing is to know how to compute the determinant. But then once in a while, I might talk about it. So let me give you an example. So imagine we have the following matrix. So let's have let's 1, 2, 3, 4, 6, 7, 8. Okay, so did some of you watch the Super Bowl? Yes. So did the team you were rooting for win or not? Yes, no. Did the team you were rooting for? No. Did you bet on somebody? No. Now let's take some bets. So does this matrix have a non-zero determinant or not? Who says yes? If these were the coefficients of some system of 3 by 3, 3 equations, 3 unknowns, would we have a unique solution or not? You know the determinant is? All right, good. So one bet here. Somebody who agrees with it. He seems like a smart guy. But you can go against him. So he says non-zero. All right. So one vote for non-zero and the other no other. So let's do it. So here the first thing I'm going to do here. You note that J here didn't say it was anything special. It could be anything. So I could pick any row or any column of the matrix to do it. So let's start with what did I? Yeah, I used that one. And of course, some choices are easier than others, but let's start with this row there, with this column there. So what I do is I compute first of all the sign. Sign is always the same. It's plus minus plus minus. Yeah, let me. So signs, by sign I mean if I must pre-multiply it by -1 or not. So for a 3 by 3. So it's like a checkerboard basically. So it looks like this. So this is 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1, 1. Okay. So if you look, for instance, row 1, column 1, well, I have as a sign -1, exponent 1 plus 1, so exponent 2. So it gives me -1 times -1, so 1. So here I have a 1. But then here, second column, first row, then 1 plus 2 gives me 3. So -1 exponent 3 gives me -1. So that's why I have a -1. So you see that there's always yeah, a change in sign each time I go down one row or right one column. And if you add a 4 by 4, then you would see the pattern is like we get -1, 1, -1, etc. Here, so 2 is pre-multiplied by -1. -1 times 2 times, and now I have the determinant of this submatrix here. So the determinant of 8, but without row, oh, right, I started with 2, sorry. So without the first row and second column. So what I'm going to do is simply remove this column and remove this row. So that's 1. Plus, now the second one here is 1. 1 times 5 times again. So what I do is there's something wrong. And then plus or minus 1 8 times the determinant of this submatrix. So here, the determinant of this we already see. So by the way, this is the same thing. So I could do it. So it's since the determinant of matrix 4 is 4, 6 is 6, 7 is 7, 9 is 9. But if it's a 2 by 2, we can just do it just looking at it. So 36 minus 42. Here, the determinant of this submatrix is 9 minus 21. And the determinant of this submatrix is 6 minus. And then let's just compute the result. Do we get? Oh, we get 0. Yeah, sorry. So that your team didn't win and you didn't win your bet. Yeah. So it turns out that I can tell you what's going on is row 3 equals 2 times row 2 minus row 1. So for instance, this is 2 times 4, 8 minus 1, 7, 2 times 5, 10 minus 2, 8, and 2 times 6, 12 minus 3, 9. But yeah, when I did that, I really intuitively, I thought, okay, there's no way that it's not 0, but it turns out it's 0. So, and by the way, I'm asking you, I don't know if it's in the last assignment or maybe a TA session, but sometimes I'm asking you, is there, find some, like, is it independent, or find some way of knowing if it's independent? So if you don't have any way, then you just have to guess more or less and try stuff to try to reconstruct one row or one column with the others. That's not always easy. But so what I'm showing you here is at least ways in which we can know for a fact whether we have a solution or not. So no solution.
Are you talking about?
Yeah.
Okay.
And yeah, so just to prove you, let's try with some other means. So not using this column there, but like this last row, for instance. So trying. So I'm going quickly here. So I would get 7 times 7 minus 8 plus 9 times this. Here I remove this and this. Here I remove this and this. Gives me 12 minus 15. Here I get 6 minus 12. Here I get 5 minus 10. 5 minus 8. And yeah. So you will have to compute determinants. Lucky you, you don't have to think, you just have to learn how to do it, and everything should go well. Yeah, so by the way, is there a easy way to compute determinants? Well, imagine my matrix here is like this, for instance. So how should I proceed to save myself some work? Exactly. So you see, if I have zeros there, then I can be smart and save time in some occasion in which I'm on time pressure to show that I know how to compute a determinant. I don't know when that would happen, but if it does, then you see that it would be 0 times the first minor, plus 0 times the second, plus minus 0 times the second, plus 9 times the third. So you save a lot of time by just having to compute 9 multiplied by the determinant of this submatrix. So that's very easy. So be smart in choosing your rows or column in a smart way. Otherwise, it takes more. Okay. Additional properties of determinant. The determinant is unique. So all of these, I'm not going to prove them. I wouldn't know necessarily how to do it. Might be easy, might not. Non-zero determinant implies linear independence. We have seen this before. Yeah, vice versa for a square matrix. So I mean, two length 10 vectors could be linearly independent. Doesn't mean that they form a linearly independent system or matrix, because you would have to have a 10 by 10. Right. So this I'm going to let you guess. It's not too difficult. So I'm just going to put this. Is that the case that the determinant of a matrix A is the determinant of its inverse, not inverse, of its transpose or not? Yeah, it makes sense, right? Yes, but since just what I have to do here is just take the transpose of this, and rather than use the last row, I would use the last column and do the exact same thing. And it's pretty obvious that all the computation would be exactly the same. So yes. Some other. So if two rows or columns are interchanged, then the determinant changes sign. Yeah, I should have thought more about this one. But I
No, but in this case, if it's a square matrix, right? Like if you look at the cofactor, like positive, negative, positive.
oh yeah, but
That is, that is, in this case, it won't change for the transpose, right? Because if you,
yeah, because it's so many things are changing at once.
Yeah.
So so it's not obvious. I can't say why this is the case. At least I don't see it obviously. But have you seen that it's absolute value? And here I'm not going to write this because it's super confusing. Yeah, the absolute value of the determinant, because we use the same symbol. So, or, yeah, let's just write it this way. So, but yeah, who cares? This is fine. Not looking for. Yeah, that's a super interesting property. I should check. Okay, that one is quite easy. Well, try and if see if you can figure it out. Or not actually not that easy. If every value in a row or column or a column is multiplied by a constant or scalar by a number, the determinant is a key. Is multiplied by a key. All these properties are obvious for 2 by 2s, but for n by n, not necessarily. And then lastly, the addition of a course instruction of a multiple of any row or column. Another n does not change the value of p. So these are all intuitive when we think about systems of linear equations. For instance, if I just add one row to another row, then intuitively it doesn't change the solution to my system of equation. However, when you think about how you compute the determinant, thinking about how this could be the case is not obvious. So I'm not going to prove anything to you. It's already done enough proving. So this is the determinant. So I'm not expecting you to understand everything right away. But so once you practice and you do some computations, then you should become good at it. We say math is a muscle you have to exercise. So questions, comments about this? Yeah.
Fully covered the class.
Yeah, that's well. That's for now. That's all I wanted to show you. Yeah. So no, that's all Laplace ever did. So, but what do you have in mind?
Because Laplace that further goes to find or something.
Yeah. So when we find the inverse, it's going to look like this. Yes.
Yeah. Once you have the determinant, you can use
All right. Conditions for singularity matrix. So one we've just seen is yeah. So or no, rather, squareness is one. The matrix must be squared. And the linear independence. So I know we had this discussion before, but so can apply either to vectors or the rows of a matrix or the columns of a matrix. Yeah. So it's rows or columns. Must be linearly independent. Yeah, I'm somehow repeating myself because I've already said it anyway. So I'll make things more concise next time. Okay, and now verifying linear independence. So one way is compute the determinant, as we just seen. Second way, a new way, is find the row form of the matrix. This looks strange. What is that? Well, it's everything we've been doing all the time when we solve linear systems of equations. It's just doing it in a more structured and formal way and organized way. By which I mean when you start with x, y, z and three equations, then what you think is, oh, me use the first two and get rid of X, and then the first and the third and get rid of X. Then I get simpler 2x2 system, and then I can get those to get rid of Y, and then I get Z, for instance. So this, you do this in a more or less intuitive way because we have always done it the same way. Well, a row echelon form of the matrix is just the step-by-step process by which you reach the solution. And if you find a solution, by which I mean you find that the last row of your matrix is not all zeros, then you're good to go. Otherwise, you're going to find that the matrix is singular. Yeah, but so just for the matrix by itself, yes. So it could be either a zero or a contradiction. Okay, so let's find the row echelon form. I'm not using that. So I'm going to tell you what you are allowed to do, and then we're going to do an example. So what you can do is, so yeah, objective. Or yeah, it's not the objective, but it's really the what is it to be in row echelon. Let's say it this way. Each row I has at least I minus 1 leading 0. So it means that the first row will have 1 minus 1, 0. So 0 leading 0, meaning the first row of my matrix is just going to be like this, for instance. But then the second row, here I have all non-zeros, but I'm going to want to have 1 0 there. And then the third row, I'm going to want to have a 0 there and a 0 there. And you see that if I get this, then for instance, it would be something like if I multiply this by some vector of variables, it would be something like 9z equals and then some vector of values. So it means that z, I get it exactly. And then I could substitute back to find y and then substitute back z and y to find x. This is the sort of thing that you would do with by doing this. So just to help you understand why we do this. So each row I has at least I minus 1 leading 0. Yeah, so each row must have at least one more leading 0. Than the previous. Yeah, and the first. So that's it really. There are just these two conditions, and then just one thing to note is first non-zero element of each row. Is called if. Note, non-square matrices can also be put in row echelon form. So it's not just for square matrices. You can do that for any matrix you like. I don't know if I don't know how much use you have for a non square matrix. Okay. And to do so, put a matrix in row echelon form. We use Gauss Jordan. So what is it? This is like solving for your linear system of equation. It's just a formal way of doing it. So here are the rules you can do for the Gauss-Jordan elimination. You can we can interchange one row with another row of the matrix. So this is like swapping equations, so it doesn't change anything. Two, we can replace one row with that row plus or minus a number another. Including itself. So it means we can also multiply one row by a number. And these are the two things we can do. So here I'm going to label the matrices A1, A2, A3, A4 just to, because there are still different matrices. And so that you know the process of doing it. So A1. So let's start with the matrix we already have. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what we can do, so what we're going to do is, so remember the goal is to replace 4 by 0 and then 7 and 8 by 0, 2. So the first thing that we're going to do is use the first row to replace the 4 by 0. And then and use also you can use the first row to replace the 7 by 0. And then we're going to use the second row with a 0 to replace this element of the third. And then we're done. So what can we do to put 0 in there with these two things that allow us to do? Yes. Yes. So row 2. So replace. Minus 4 times row 1 plus row 2. So what do we get? So minus 4. And then this would be minus 8. And this would be minus 12. So here I get 0. Minus 3. Minus 6. Step 2. Let's ask somebody else because I know you know the answer. So step 2, I'd like to, oops, and this would be A2. Now I'd like to get rid of this 7 there. So what should I do? What I'm allowed to do is to add any rows and any multiple of any other rows to this row, for instance. Here, what we just did is we took this row, we multiplied it by -4, and we added that to the second row. So we got this result with 4 minus 4. That's what we were looking for. Here we're looking for a 0 in this cell there, in this no idea. Even the chat be
Maybe you can align between how like if you get from row row two. Like for me it's good, but I guess like.
So do you want me to just okay. Okay. All right. That's what you're saying. This is 4 times 1. This is 2 times 4 times 2. That's what you were suggesting. Yeah, so it's just for me it's super easy to copy that. For you it's long, but yeah. That's good. That's good. So any idea for the 7? No? Yes? Yes, good, thank you. So replace row 3 by -701. That's row 3. So here I'm going to call the new matrix A3. So -7 times 1, -7 times 2, -7 times so I get 7 minus 7, so that's so 14, so -6, and then -21, so I get -2. If I'm not mistaken, right? I gave you some time to copy that. Yeah, and then I'm almost there. So what I want is to have in the last row, I want to have one more 0 than the previous row. So what I want to do is to get rid of this -6 here. So A4. So somebody has an idea of what we should do? Somebody new wants to participate in the class? This live, yes. Interactive. Yes? Yes, yes, exactly. So multiply, so replace row 2 by -2 times row, sorry, row 3, yeah, by -row 2 plus row 3. So I get 0 -2 times 0, -2 times and -2 times -6. So what do I get? I get that's 0. So that's why we had to deal with this row before that one, because now we don't mess up the work that we did before. So we since this is a 0, we can multiply it by anything. It's still a 0. So here we have 0. Here we have 0 by design. And here we have minus 12 plus 12, so we have 0 again. So we see that indeed our intuition about the determinant being 0 was right, because after Gauss-Jordan elimination, we find that the last row is all zeros. So it looks like essentially I was missing a row, but I didn't see it initially, because in this way it's not easy to see that your matrix is singular, but it is. Yeah.
Inclusive of the zero of the bottom line, it was a number of 8. Okay, I got an example.
So if I start with something, yeah.
So you have like 1, 0, 0, 5, 0, 3. Then I don't know if because I'm recalling something from the context, but can you multiply that with the diagonal to get the determinant? Or
Yes, exactly.
yeah.
Yes, yes, yes. Yes, okay. So actually that was an exam question that I gave last time. And most of them got it, so I was quite pleased. Okay, so the suggestion is the following. Yeah, so let me just check my. So the question was if the matrix is upper triangular, then how can you easily show that the determinant is the product of the rows of the element? Yeah. Okay, I'm going to do that, but I wouldn't know if because you can't do anything with these are two things, like the determinant might change. Yeah, so if two rows are interchanged, then the determinant changes sign. So yeah, then also I haven't prepared for this sort of discussion, so I'm not going to take too long. But no, it's interesting. But one thing I can see right away. So trick for the determinant. So what we were discussing is the following: if a matrix is upper triangular or lower triangular, but upper triangular meaning it has it's Gauss-Jordan. Yeah, it's so it's it's row echelon form. Is identical to itself. Then, so look at what happens. So if I have, for instance, this matrix there. Oh, by the way, this is sorry. This is I had been using the wrong sign all along. So, yeah, these are square brackets. So now I understand why you were confused. My bad. Okay, so now it makes sense. So if I have this and I'm computing the determinant, so it's equal to let's take so the determinant of this matrix. Let's take the first column. So it would be 1 times the determinant of this smaller equation, smaller matrix there. And it was, so what is the determinant of this matrix there? Then it's just -3 times the determinant of this small matrix there. So it's -3 times the determinant of this small matrix, which has a single element. Oh. So it's just, yeah. So it would be minus 3 times 3, so minus 9. So upper triangular means it has elements that are non-zero on the diagonal and on the top elements, but below the diagonals, they're all zero. So if that's the case, then you can see that a very neat way to compute the determinant is just to compute the product of the diagonal elements. Product. Diagonal. Yes, I was mad enough to ask this at the exam. Okay, so that's row echelon. Now I have heard somebody, I'm not going to name, in the room who talked about reduced row echelon forms. So let's just say a few words about this. So if matrix A is in reduced echelon form, each pivot must be 1. And all elements about the pivot must be 0. So let's continue with our example. So we had A4 here. So let's have, I'm just going to go quickly. This is not super important, but is in case you hear it at one time, then it's good for you to know. So then next step, well, I'm going to get rid of this 2 over here, thanks to this minus 3. So I'm going to replace. Plus 2 terms. So here I'm going to get plus 2 thirds times 0. Plus 2 thirds times minus 3. And plus 2 thirds times minus 6. So then I get this. So this is still 1. And this is 2 minus 2, 0, as I wanted. This is 6 times 2, 12. Yeah, so minus 3, I think, or minus 1.
Oh, yeah.
Yeah, and then let's just set this to replace minus 2. So here all I'm doing is essentially multiplying row 2 by minus 1/3 to get a 1 here. A6. One. Here I get this is a minus so 2. So the row echelon form in general is not unique. There are many different row echelon forms that we can have, but here know that the reduced row echelon form is unique. Also note if starting matrix is non-singular, it's reduced row echelon form is what? It's a special matrix. Non-singular means you get a singular, yeah, you get a unique solution. It has an inverse. The determinant is positive or negative, non-zero. So if it's the case, then I would have had a number here. So I would have been able to get rid of this and this as well, and then multiplied it, and I would have gotten the identity matrix. Simply. So I'm not going to go into more detail for the reduced row echelon form. If you stop here and if you find, for instance, this form there, and you know you have a row of 0, then you're good to go. You know that there's something wrong with the starting matrix. All right. Question about this? Comment? Maybe if I'm going too fast, sometimes you can say, please, I need more time to copy stuff. Otherwise, I barge it. Franco matrix. So those bullet points. The rank of a matrix A is defined as the maximum number of linearly independent rows or columns in the matrix. And we note it R of A. Yeah, so this is super definitional. Sorry, we just had to go through this. So a matrix A n by n that has a rank as the minimum of m or n is characterized as full rank. So what does that mean? Well, it means, let me give you 5 seconds to copy that. And then I'm going to show you what I mean by this. So if I go back here, so this matrix wouldn't be full rank. Yeah, I can, yeah. Example. This matrix is not full rank because it only has 2 independent rows, but is 3 by 3. But if I say, oh, this is a stupid matrix because it's not full rank, so let me get rid of this useless row there, then this is full rank because it has 2 independent rows and is right. So here the rank is 2, and yeah, and the rank is 2, and the minimum of 2 and 3 is 2. So let me continue with my questions. You use row echelon form, Gaussian matrix. Find the rank of any matrix. So the Gauss-Jordan elimination is a way to get rid of everything that's superfluous. So you get to the essential of what the information you have in your matrix. So that way we're able to know that we have just 2 rows that are independent of each other, and the third one can be eliminated. So maximum number of linearly independent rows in a matrix is equal to the number of non-zero rows in its Gaussian matrix. If A is an n by n matrix, and the rank of A is n, then so it's By the way, it's full rank. Then the determinant of A is non-zero. And the inverse is. So the matrix is non-singular. Therefore, the system AX equals B has a unique solution, which is X equals A minus 1. So how do I find this? Well, it's just that I start with AX equals B. So I pre-multiply by A minus 1 on both sides. So I get A minus 1, A minus 1. I can do that. And here I get the identity matrix. If you find the inverse, then you already have your solution. So is that a trick to go faster? Well, no, because finding the inverse takes time. So you're not getting around doing some work. A minus 1 can be hard to compute, but obviously we're not going to see this today, but probably next time. But that's a neat one. That's useful for some exercise. R of A equals to is smaller or equal to the minimum of RA and RD. So this essentially what we're saying there is if you start with a low rank matrix, then you cannot multiply it by something very, very big and hope to obtain something that's higher ranked. You still have the minimum information that was inside your first matrix or inside your second matrix. So if I give you an example, so for instance, you remember the outer product, which has a vector multiplied by a column matrix multiplied by a row matrix, or column vector multiplied by a row vector. So you get a very large square matrix, for instance. Well, you don't get higher rank than what you started with. So here you would get a rank of 1. Yeah, so let me give you some insight into this last property. So just not a proof, but illustrative example. So imagine consider a rank 2 matrix. A equals let's have A1, A1, A2. And a rank 1 matrix. Which would be something like, so imagine that I don't have enough information, so I just have C1, C2 and 0, 0. So if I compute the product, what do I get? So AB equals to so that's A1 times C1. Here that's A2 C2. Here that's B1 C1. And here that's B2 C2. And obviously what you see is that so if you look at the columns, for instance, then it's just A1 B1 times one coefficient, and this is it A2 C2 times another coefficient. A1 C1, A2 B1 C1. B2. Oh yeah, B1. Sorry. Yeah. It's, otherwise, my example doesn't work. So that's A1 C2. Yeah. That's the problem. Yeah. Okay. Thank you. For yeah. So now it works. So here you see that you have A1 B1 and A1 B1. So you have the same thing essentially. It's just multiplied by a scalar, and so that's exactly our definition of linearly dependent. Row, or let's just say column. Is 1 times let's col 2 is col 1. So exercise for you. Compute. The same thing, just try A B prime. So just to confirm that it doesn't matter if you flip B, you're going to get again something that is as a. All right, so I'm absolutely stopping here because I've given you so much stuff. And next time we see the beast matrix inversion. So there's no increase. Oh, this is a vector. I'm saying it comes from. Oh yeah. Therefore, the system AX equals B. X is just a vector of variables as a unique solution, and it's X which is equal to A minus 1 by B. So, did you miss that thing or?
I just thought this is the second step for this one. So they are not related.
Yes, so so you just missed, see, has a unique solution. You just need to add this. Therefore, the system AX equals B. Add it's going to make sense.